And I'm delighted to introduce Thomas Blom to talk about the chain rule in Goodwillie calculus.
Thank you very much for the introduction and for letting me speak here. Yes, I'll be talking about the chain rule in Goodwillie calculus. All of this is joint work with Max Planck. So in classical calculus, in classical calculus, there's this formula that is often referred to as the finite Goodwillie formula. And it's something, the chain rule in calculus is about, well, it tells you how to compute the derivatives of the composite of two functions in this way. Like, we all done this from a very long time ago, I assume. And then there's the product rule, which tells us how to compute the derivatives of the product of two functions. So if you combine these, you get, and you do some clever counting, then you get a formula that looks like this. So the nth derivative of a composite of two functions, you can write it as a large sum over all partitions of the n element set, then whatever is there. So the goal today will be to establish such a formula in Goodwillie calculus. And well, we'll kind of succeed. So let me just mention the following convention that so from now on, I will just assume that all my categories are infinity categories and that they have these properties. So they are presentable, it's like co-complete, completes, and other niceness properties. They have an object which is both initial and terminal, so that's usually called pointed, and tilde co-limits need to commute with finite limits in C. And yeah, such an infinity category is sometimes called differentiable, although sometimes this means something else. Well, yeah, I think I've tried to always write infinity category in the slides, but if you hear me say category, then it will always mean infinity category as a disclaimer. So we saw today that in the Goodwillie, that in Goodwillie calculus there's this tower, the Taylor approximation to a functor f. And if we have a tower like this, we can always look at the fibers, and well, those are usually called the layers. And these layers, they are so-called n-homogeneous functors, as we saw today. So they are n-excited, and they have this property that if you take the n minus first excited approximation, then you get a point. So there's a result by Goodwillie, and well, in this more general form stated by Lurie, that if you have a functor which preserves the zero object and tilde co-limits, then you can for every n write on some symmetric functor. So it's a functor of n variables, which is symmetric in the inputs from the stabilization of C to the stabilization of D, such that there's a formula. There it is. Such that there's a formula like this describing the n-homogeneous layer in this form. So this is a slightly different formula than we saw today, and that is because well, if this here is spectra and this here is also spectra, then this formula can be simplified a bit, and you can actually show that everything is determined by spectra with a sigma n action. If you want to have a more general formulation, you need to state it like this. So we'll just call the nth, this partial n of f, we'll just call it the nth derivative of f. So these are the objects for which we want to prove a chain rule or a Fadi-Bruno formula. So I will start by describing what I like to call Lax structure on the derivatives. So because the Fadi-Bruno formula involves different types of derivatives of so it's good to have some large category that contains all the derivatives of a functor. So we want to take all these together, and we call these functor symmetric sequences. And the functor symmetric sequence is really just, it's a sequence of functors where the nth functor has n different inputs one output, and it's symmetric in the input. So that's what this these homotopy orbits there indicate. So we'll call those functor symmetric sequences. If we assume that all our functor symmetric sequences, that they in each variable produce that they are reduced and finitary, so they preserve the zero object and fill their colimits, we'll call them we'll put like an asterisk and an omega there. If they preserve all colimits in each variable, we'll just put a little L there. Yeah. It's just notation, nothing deep going on. So the derivatives, if you take all the derivatives together, they just give you a functor from this category here. So reduce finitary functors from C to D to these functor symmetric sequences. And one thing one can show about the functor symmetric sequences, if we go from some category C to itself, is that there's a monoidal structure which is called the composition product, and which informally satisfies this formula. So this formula is very reminiscent of the composition product of symmetric sequences used to define operads. And as you might notice, it also looks a lot like the Fali-Bruno formula. So, the goal that I said about proving the chain rule, we can refine it or reformulate it as saying we want to show that this functor is strong monoidal. So that is actually a stronger statement than just having a formula, because it also allows you to translate the things about, say, monads from one side to the other. How do you show that a functor is strong monoidal? I mean, it's extra structure you need to construct. And often this is quite hard. So usually it's a bit easier to construct an lex or an oplex monoidal structure and then try to show that it is actually strong monoidal. And how do we construct a lex monoidal structure? Often you just observe that there's some left adjoint, which just happens to be oplex monoidal for whatever reason. And it turns out in practice this often works, but it doesn't work today. So that's very unfortunate. Because there's no left adjoint. However, there is a factorization. So we kind of saw this today already. So if we take the Goodwillie derivatives, you can compute them by first taking cross effects. So this is all the cross effects for all n taken together. And then you do this multilinearization procedure. So you apply P1 in each variable separately. So the derivatives as a functor, they factor in this way. And now it turns out that there's a left adjoint here, which I will come back to in a moment, and there's a right adjoint here. So it's quite close to the ideal situation that I sketched. It turns out that this functor here is a localization, so there are good criteria to check when a localization is compatible with a monoidal structure. This lambda here, this actually has a very explicit and quite simple formula. So you have some functor symmetric sequence, you want to get an actual functor out of it. So what do? Well, you take an object, you just plug it in every variable. You have this symmetry, so you mod that out, and it gives you a functor. And this turns out to be left adjoint with these cross effects. You might think, well, we're good to go, but we're not. Because if you want to show that both these functors are monoidal and then conclude the statement, then the middle category needs to have a monoidal structure, and it doesn't. And the reason is that this composition product that I suggested is not associative. The reason being that there's this co-product here. There's a finite co-product, and if you want associativity, then all the functors, they need to preserve finite co-products in each variable. So that's too bad. But it turns out there's a very easy trick to work around this, which is unfortunately harder to implement than we thought at the start. Then we would just add them. So instead of working with actual co-products in this category, we just enlarge the categories by formally adjoining colimit finite co-products, and then we work there. So the idea is that we define we the function category that's called P-fin of C. It's something like taking pre-sheaves and then localizing. And it has the property that colimit preserving functors out of it are the same as finitary reduced functors out of the original category. So, well, we can look at that category and we can put it here. And here we are going to have an associative composition product. Now, the Uneta embedding gives you a fully faithful inclusion here. Because we already had these colimits that we added in a formal way. There's a left adjoint, we can go back. And because the Uneta embedding is pretty faithful, going to the bigger category and going back doesn't really do anything. So we can instead look at the composites of the cross effects with this iota and the composite of P1 with L. So I've denoted these with a twiddle. And now we're now we're in a good situation because this actually has a monoidal structure given by this composition product. And we have these cross effects here, and we have this P1 here. And it turns out that we still have these left and right adjoints. And it also turns out that this P1 here is still a localization. So, oh, that's too fast. So one can show that these cross effects or the cross effects with the twiddle, that it's lex monoidal. So this functor lambda, which is, well, defined as the same way as the previous one, essentially. One can show that this is op-lex monoidal, so that its right adjoint is lex monoidal. And, well, it turns out that this P1 is not strong monoidal or lex monoidal, it's op-lex. So usually that's bad when you compose a lex monoidal functor and an op-lex monoidal functor, but it turns out that it's actually strong monoidal on the image of iota. So yeah, that's good enough to make it work. And well, that leads to the result that the derivatives can be made into a lex monoidal functor. So that doesn't give us a chain rule yet, but at least now all the extra structure that we needed, all the coherencies are there. Now we just need to check that we actually have a chain rule, that the lex comparison maps that we have are actually equivalences. So, so yeah, the result that we have there is that if C is stable, then this lex monoidal structure that we have is actually strong monoidal. So there's a natural equivalence of this type. So here, this is the composition product, which is this Fadi-Bruno formula, and on the left we have the composite of G and F. So let me say something about the history. If C is the category of spectra, then this was already proved by Michael Ching, or at least like the equivalence here was proved. The fact that this is strong monoidal, it's hard to deduce, like because it really relied on a certain model, and model categories don't interact well with functor composition usually. So you can't really derive that monoidal structure to get to get a statement of this kind. And there's another slightly different proof by Ronching that was proved later. And well, the main strategy is that now we have this, the lex structure gives it a comparison map like this. So essentially the strategy of the proof is to do a series of reductions, which allows one to look at the specific case where G is homogeneous and F is a finite coproduct of homogeneous functors. And this is, in this case, everything becomes explicit enough where you can just check by hand that the comparison map that you have is an equivalent. But this is only the stable case. And unstably, I mean, the chain rule actually fails for quite obvious reasons, namely that the derivatives of the identity is generally not the unit in symmetric sequences. So, however, this is when you have a failure like this, one thing you can try is you can just try to somehow model out the failure. So there's this construction of the relative composition product if you have two bimodules, and you can try to do that here if you have that you can define if you have the derivatives of the identity and you have a left and right module over it, you can define this bar construction, which is a version of the relative tensor product. And explicitly, it's some geometric realization of this type. And well, if we do this, then at least this problem here goes away. Like we've just literally defined it away. So one might hope that we get some kind of corrected chain rule where so you get a map like this essentially from the Lex structure. So this by definition, this relative composition product is the bar construction. Now the Lex structure on these derivatives allow us to put them outside together with the fact that bar is a colimit. And then, oh, what is the bar construction of, well, when you put the identity in the middle, it's just the actual composition. So you get a map like this. So the question could be that, well, the next best guess would be that this map is an equivalence. And in the case where we work with pointed spaces, this was proved by Aaron Ching. Not specifically for this map, but they showed that there's this equivalence where you use the relative composition product. And in general, we showed that this is in general the case. So if we have functors between differentiable infinity categories that can be composed, then this map that we get from the Lex structure is actually an equivalent. So it's the next best thing to a chain rule. And in particular, what this gives us, because we already have this Lex structure, we can lift the functor. If we look at endofunctors from some infinity category to itself, we can lift it to bimodules of the derivatives of the identity. And like one way of rephrasing this chain rule is saying that when you do this lift, you get a strong-monoidal functor with respect to the relative composition product. So yeah, that's the result. As I already said, like a similar thing was established by Aaron Ching. If you work with pointed spaces or spectra, and let me just, I mean, there's not really time to talk about the proof, but let me just mention that the key ingredients here are essentially one wants to reduce this statement to the stable setting where we already have a chain rule. And well, one way of somehow interpolating between stable and unstable homotopy theory is to build resolutions. And like there are very canonical ways of doing this, like so-called Bousfield-Kahn resolutions. And the idea is to somehow resolve all our functors using these Bousfield-Kahn resolutions and then apply derivatives to this. And then, well, one observes that this type of Bousfield-Kahn resolutions, it becomes a form of causal duality on the level of symmetric sequences. And then using facts about causal duality, one can actually deduce this unstable chain rule. So let me say a bit about operads and some applications of this and examples, because well, operads and calculus, this workshop, so seems fitting. And so if we look at the case where C is the category of spectra, then symmetric, these functor symmetric sequences that preserve colimits in each variable, they are actually symmetric sequences in spectra. And because, well, we don't have anything in arity, we don't consider things with arity 0, so what we get is symmetric sequences that are concentrated in degree 1 and up. So if you look at algebras in there, it's going to give you the category of operads enriched in spectra, or at least uncolored, reduced, uncolored non-unitary ones. So we now have a machinery that's such that if you start with some category C whose stabilization is spectra, and you apply the derivatives to endofunctors, you will get symmetric sequences. And if you plug in a monad, you're going to get an operand. If you're already stable, then if you plug in a comonad, you're going to get a co-operand. And these are things that you get for free from the Lex structure. And this has always been, let's say, some kind of guiding philosophy in Goodwillie calculus, that it allows you to somehow translate between monads and comonads on one side and operads and co-operads on the other side. And it allows you to decategorize some statements, to statements about operads and bimodules. And well, let me give some example, which is not exactly of that kind, but one thing you get is that for any monad on pointed spaces, its derivatives, they form an operad in spectra. So one thing you can show is that the derivatives of the identity, it gives you an operad because the identity is monad, that it's causal dual to the derivatives of the comonad sigma infinity loops infinity. And one can show that this is the non-unital co-commutative co-operad, which means that well, essentially by definition, this is what is called the spectral Lie operad. So that one is usually defined as the causal dual of the non-unital co-commutative co-operand. So one thing you can observe is that Snaith splitting tells you that on connected spaces, there's an equivalence of this kind. So now you can say, well, let's hit this with derivatives and see what we get on the level of symmetric sequences. And it turns out it gives you a formula of this kind. So if you take the relative composition product over the Lie operad of the unit with a shift of the Lie operad, then you get the non-unital En operad. And I wouldn't know an easy proof of this just at the level of symmetric sequences. I think Connor told me he once observed this too, but it's quite neat that this just follows from Snaith splitting. And a little bit more can be said. So if you look at the following map, so you start with loops and sigma n, and you apply the unit to get here to loops infinity, sigma infinity, loops and sigma n. Well, Snaith splitting tells you it's equivalent to this. And one can actually show that this is a map of monads. So this is not obvious at all, at least to me. It was not obvious why this would be a map of monads, except that it's, well, I was hoping it would be. So I sat down and it's, I mean, if you formulate it like this, it's not so easy to see, but there's also this operatic reformulation of the Snaith splitting by Cohen. And if you use that reformulation, it's not so hard to observe that this is actually a map of monads. So if you take derivatives, you'll get a map of operads. And this is, well, you can show that the derivatives of this is just the shift of the Lie operad. So you get a map from a shift of the Lie operad to the non-unital En operad. And such maps, such maps have been constructed before in different ways. And the idea is that these should somehow give you a way of defining kind of higher enveloping algebras. And so what we suspect is that this map is causal dual to the inclusion of the non-unital En operad into the non-unital E infinity operad. And similarly, you can also apply Goodwillie derivatives to other things. And well, another example in the same vein is you can apply it to this co-assembly map, which is going to give you a map of this form. So a wrong-way map between En operads. And we suspect that this is causal dual to, well, the usual inclusion of the En into the En plus 1 operad. And like these wrong-way maps, like they are surprisingly hard to construct. Like Michael Ching and Salvatore, they have this paper where they actually give a quite explicit construction. And if you read May's geometry of iterated loop spaces very carefully, like at some point he needs to compare En algebras with algebras over this monad here. And essentially, if you look very carefully at what he does there, he is actually secretly constructing the wrong way map. I'm almost finished. So he's actually secretly constructing the wrong way map. And I believe that that is why these wrong-way maps show up in Goodwillie calculus, because somehow secretly when you're doing the snake splitting stuff, you're secretly using maze recognition principle, which is somehow involves this wrong-way map in, but it's hidden in the machine. And seems that Goodwillie calculus gives you a way of extracting it. Anyway, that's actually all I wanted to say. So thank you for listening.
Yeah. So the first mark, the one from here plus one to identity by one, it keeps the bracket and kills the commutative product, right?
I think so.
So
I'm not an expert on
okay,
that.
so the
What
dual,
happened?
because the cosine dual will keep the commutative product and kill the bracket in some sense. So I don't know if it has a sense to see what you are saying about it or not.
Yeah, I think it does, but I don't know. I'm sorry.
You're exactly right.
Okay.
That's compatible with the maps in.
Okay.
Thanks.
Can you say some stuff about like the unitary end?
The unit all Ian. No, not really. So the issue is like with the calculus, like you need to assume that your functors are reduced to get a chain rule like this. And if your functors are reduced, then this just tells you that, I mean, you can't really, in degree zero, you don't really have derivatives. Yeah, some of the symmetric sequences that you're gonna get, they're just not gonna have anything in degree zero. So you can't say any unital thing. Max, my collaborator, is like he has been thinking about something involving what are called dual derivatives, and there it seems that you can actually say something about unital operands. But that's still quite speculative.
We should, once again,